Hi again, welcome to day 19. Today's episode is brought to you by a small g, and as you can tell, what we're going to take a look at today is the relationship between gravitational field and Newton's law of universal gravitation. Here's a scenario for it. Suppose we have a big mass like the Earth and a smaller mass like a GPS or weather satellite, or maybe even the moon orbiting around it. And obviously there's going to be a force of gravitational attraction between these two masses. They're going to be pulling each other towards themselves with that much force. But the question is, what's the gravitational field way up here where this thing is orbiting? On Earth, we know that the gravitational field near the surface is 10 newtons per kilogram. But what is it way up there when you're quite a bit away from the center? And you have to remember, force of gravity is just how many newtons are pulling. The gravitational field is how many newtons are pulling on each kilogram. And that's the one that we're interested in. How can we calculate gravitational field when you're quite a ways away from the center of something? Let's see if we can develop an equation that will allow us to figure that out. Well, what do we know about this situation? Well, we know for sure that Newton's law of universal gravitation applies. We know for sure that the force of gravitational attraction between these two things is going to equal G times one mass times the other mass divided by their center to center separation, all squared. Okay, what else can we do here? Well, remember, the force of gravity on something is going to be equal to its mass times its gravitational field. I think everyone's going to agree with that. You've seen this equation dozens of times, maybe even hundreds. The force of gravity on something is equal to its mass times its gravitational field. Okay, so let's just make that substitution over here. The force of gravity on something is equal to the mass times the gravitational field it's in. And on the other side, we still got G_mm over r squared. Look at this. We got a small m here and a small m here. We can divide both sides by small m. Basically, these two things annihilate each other off the face of the Earth, and you're left with this. There's a handy-dandy little equation. Little g is equal to big G, big M over r squared. There is an equation you can use to figure out the gravitational field of something as you get further and further away from its center. Gravitational field is equal to G_m over r squared. Now, one thing you've got to keep in mind here, this mass, okay, it is the mass that is causing the gravitational field. It's not the mass that the gravitational field is in. This is the mass that is causing the gravitational field way up there. So let's maybe make a little note of that. This m is the mass causing G. It's not the mass that G is in. All right, we will be back in just a second, and we will do an example problem involving example to take a look at. Find the altitude of a communication satellite that stays in a geosynchronous orbit. And a geosynchronous orbit is one where the satellite stays in the same spot above the equator. Let's talk a little bit about this idea of a geosynchronous orbit. Think of all the satellite dishes you see around town. These satellite dishes, they have to track these satellites which are orbiting the Earth at a tremendous velocity. But you never see anybody outside taking their satellite dish and moving it like so, trying to track the motion of some satellite. Basically, if you have a satellite dish, you just point it towards the satellite and don't worry about it. You don't have to worry about trying to track its motion across the sky. That's because communication satellites, the ones that carry our cell phone signals and our TV signals, communication satellites, they are in this thing called a geosynchronous orbit. Here's how that works. Imagine I'm the Earth, and let's say right there is the equator, and of course the Earth rotates on its axis, on its axis. And if a satellite is in geosynchronous orbit, okay, it's going to be right above the equator, and it's going to be orbiting just like that. Okay. It's going to be orbiting so that as the Earth rotates, that satellite, it stays above the exact same spot over the equator. So no matter where you are on Earth, like if you're over here, you just have to point your satellite dish to that same spot and you got it covered. Okay, so I think we are ready to do this problem now. Find the altitude of a communication satellite that stays in a geosynchronous orbit. Okay, so here's a diagram of the situation. There's the Earth with a mass ME, there's a satellite with a mass MS, and of course the center to center, the separation between the two, we're calling that R. And what we really want to find out is the height of the satellite above the Earth's surface. And let's face it, if we can figure out what the center to center separation is, the height's a piece of cake after that. It's going to be the center to center separation, take away the radius of the Earth, which is in that table with the Kepler's laws hands out. You do that subtraction, and there's the height of the satellite. Okay, how can we do this? Well, a lot of people, they automatically think, oh, Newton's law of universal gravitation. Okay? This thing attracts this one with some force of gravity F.G. And we know that F.G. is equal to big G times one mass times the other over the center to center separation, all squared. Okay, looks promising. Looks like we might be able to solve this for R. But if you look at it closer, we have no idea what the force of gravity on this satellite is. We have no idea what the mass of the satellite is. And we're trying to figure out what R is, so that's not going to work. So we need something different. How can we do this? Well, you got to remember, this satellite, it is orbiting the Earth. It's actually an ellipse, but that ellipse is pretty darn close to a circle. So this satellite, it's moving in a circle. That means it is accelerating in towards the center of the circle. Remember from the video you watched yesterday, okay, that satellite is free falling around the Earth. So if something's in free fall, the acceleration is equal to the gravitational field. Make sure you're okay with that. This satellite is moving in a circle around the Earth, therefore it's accelerating towards the center of the Earth. That's a centripetal acceleration. And also remember from the video yesterday that it's in free fall. The only force acting on it is the force of gravity. So that means the acceleration is equal to the gravitational field. Now what can we do with this? Well, we know the acceleration is a centripetal acceleration, which is v squared over r. The gravitational field, way the heck up there, way above the Earth's center, is going to be g times the mass causing the gravitational field over the center to center separation squared. Okay. And what can we do here? Well, we got an r here that'll cancel one of these r's over here. And Okay, great. I want to solve for R. Perfect. Big G, I know what that is. Mass of the Earth. I can look that up off the table that came with Kepler's laws handouts. What's the velocity of this thing? Okay. Well, you got to remember the magnitude of the velocity is going to be how much ground this thing covers over the course of one revolution. That's basically going to be the circumference of the circle it's following, 2 pi r. Divided by how long it takes to go around the circle once. We'll call that big T. That's how long it takes to go around once. Okay, so let's make this substitution. Okay, V is equal to 2 pi r over t. So I got V squared. So that's going to be, if I substitute 2 pi r over t in for V, I get 2 pi r over t all squared, and that's going to be equal to G M-E over R. And we're running out of space. We'll be right back with a little more space created. Okay, so here we are, still doing this problem, still working through the algebra. Remember, we know that the acceleration due to gravity is the same as the gravitational field, and the acceleration is centripetal acceleration towards the center of the circle, V squared over R, gravitational field, G M over R squared. An R on this side cancels with an R on that side. So what you're left with is V squared equals G M E over R. Remember, the velocity of this thing as it's going around the circle is equal to how far it goes over the course of one revolution, the circumference of the circle, 2 pi r, divided by the time it takes to go around the circle once. So you make that substitution. V squared is going to be equal to 2 pi r over t squared. There it is. I substitute in that for V, and it shows up over here, and that's equal to G M-E over R. And then it's just a little bit of algebra. 2 squared is 4, pi squared is just pi squared, r squared is just r squared, t squared is just t squared, and the other side doesn't change. Now remember, we're interested in r, so let's solve this equation for r. So let's take this r over to the other side, and it's going to go upstairs, and you're going to have r cubed on this side. The 4 pi squared is going to go over to the other side, and it's going to go to the basement. The t squared is going to go over to the other side, and it's going to go to the top floor. So there's how you're left, or pardon me, there's what you're left with right now. R cubed is equal to G M-E-T squared over 4 pi squared. We're interested in r, so take the cube root of both sides. The cube root of r cubed is just r, and then we got the cube root of all this mess here. Okay. Let's take a close look at this mess here. G, gravitational constant, we know what that is, 6.67 times 10 to the minus 11. Mass of the Earth, I think it's 5.98 times 10 to the 24th. It's on the table of solar system data with the Kepler's laws stuff. Okay. 4, that's easy. Pi squared, that's easy too. T squared, okay? Remember, T is how long it takes this thing to go around once. What's that going to be? Okay. That might seem like a bit of a snag at first, but think about it. Remember, this satellite is in a geosynchronous orbit. If I'm the Earth and there's the equator, this satellite is always staying at the same spot above the equator. So it takes the Earth 24 hours to spin around once. That means it's going to take this satellite 24 hours to complete one revolution. So we know what T is. We know that T is equal to 24 hours. Of course, we got to convert that to seconds. So 24 hours times 60 minutes in an hour times 60 seconds in a minute. Real quick, let's just do that. comes out to 86,400 seconds. So all we have to do now is plug in all the right numbers into this equation, including t, 86,400 seconds, and there's going to be our answer. We'll be right back with that. So we're getting close to the end of this thing. We know that r is equal to that mess, and substituting in for all these numbers, gravitational constant 6.67 times 10 to the minus 11. The mass of the Earth, you can look that up off the table of solar system data that's in with the Kepler's laws handout, 5.98 times 10 to the 24th. T, how long it takes our satellite to go around once. Well, remember that's 24 hours, and we worked it out to be 86,400 seconds. Don't forget to square it. And of course, on the bottom, we got 4 pi squared. You grind that through your calculator. Hopefully you get, please get the same thing I do. Hopefully I didn't make a mistake here. 4.2 times 10 to the 7th meters. And remember, that is r, the center to center separation between the Earth and our satellite. Of course, what the question is interested in is what's the satellite's altitude? What is its height above the surface of the Earth? So that's easy enough. You just take the center to center separation, subtract away the radius of the Earth, and there's your height going to be left over. Did that right here. The height, center to center separation, take away the radius of the Earth, and again, you can look that up on the table of solar system data in with the Kepler's laws assignment. So center to center separation, take away the radius of the Earth, and you get 3.6 times 10 to the 7th meters. Please, I hope you get 3.6 times 10 to the 7th meters. I hope I haven't made a mistake. I don't think I did. Okay, now just how high is that? Okay, is that like skimming the surface of the Earth barely, like the International Space Station? Let's just take a second and see if we can figure out just how high that is. And without doing any super complicated calculation, how about this? There's the radius of the Earth, 6.3 times 10 to the 6. The height of this thing above the Earth is 3.6 times 10 to the 7th. Look at this. This is times 10 to the 7th. This number is times 10 to the 6th. So this exponent is bigger than this one by 1. That means this number is, roughly speaking, 10 times bigger than this number. So if this is the Earth, and there's the radius of the Earth, the height is going to be like 10 times 1 Earth radius. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, it's going to be like way up here. So that kind of puts it into perspective. How high up are these satellites in geosynchronous orbit? Okay, well, if this is the Earth, relatively speaking, they're about that high. They're a ways away. They're not like this International Space Station just skimming the surface. Okay, so if you can figure out how to put a satellite up to that exact height so it stays in the same spot above the equator, if you can do it for less money than Elon Musk, you're going to make a lot of money yourself. As far as an assignment is concerned, I will post one on this, and you probably want to have it done for tomorrow, because we're going to be taking a look at, it could be the last topic in the unit, or at least pretty close tomorrow. Bye for now.